Hello and welcome to a special episode of Solidworks Live. If you joined us last week, we discussed design for additive manufacturing with a special guest, Paul DeWys from Forerunner 3D Printing. I welcomed him back here again today to answer some of the many questions we had last week. Paul, welcome back to Solidworks Live.
Hey, Jeremy, thank you so much for having me back.
So, Paul, we covered a ton last week, and we mentioned during the stream there were a lot of questions coming in. So many we couldn't get to even a fraction of them. I have over 3 pages of questions. How do you feel about just kind of going through and answering some of these questions today?
That'd be great. Let's do it.
All right. So I talked to you about this ahead of time. Paul has not seen any of these questions. He specifically asked not to see any of the questions because he didn't want to get any preconceived ideas of how he'd answer those ahead of time, correct?
Yep.
All right. So we're going to dive right in. These are in no particular order. If you haven't had a chance to watch that previous SolidWorks Live episode, we'll put a link down in the description below where you can go learn all about additive manufacturing with Paul. But Paul, I'm going to dive in. Some of these, keep in mind, I'm reading most of these questions verbatim as they were copy and pasted. So some of the language may be wrong. We'll go through these together, Paul.
No problem.
All right. So the first question is, what stereolithographic do you use for these prototype prints? And I think the question they were asking is, what type of 3D printing process do you use? You early on in the episode had some like translucent prototypes, right?
Yeah. So for stereolithography, we run a 3D Systems SLA 5000, and that machine is capable of swapping vats, so we can switch which materials are inside of it. So for material, we run DSM. Well, they just got sold. I don't even know who owns them now. We run what used to be DSM Watershed for clear parts, and then for white parts we run DSM Next. So those are the 2 SLA materials that we run in that 3D Systems machine.
Okay. All right. Okay. So Paul, you sort of answered this next question a little bit there. One of the other questions we have are, what are some of the materials we can use for 3D printing? And this is very general. This is not machine specific.
Yep. So there is a massive variety of materials. So there's really 2 kind of classes of materials that I would break it down into. So you have desktop printer materials. So this would be like for your desktop FDM machines like MakerBots, or desktop SLA or DLP type machines, which would be like Formlabs or kind of that type of printers. So you have the kind of the desktop variety, and then you have more of the industrial variety, which would be like, our MJF machine or our 3D Systems SLA, our FDMs from Stratasys, PolyJet, Clip. And so inside of each one of those categories, for desktop FDM and desktop SLA, there's got to be hundreds of materials for those. Every week I'm getting emails from companies all over the world that are releasing new materials that do all kinds of crazy things, whether it's like rubbers or ESD safe materials that dissipate static, or like super plastics like PET or PEEK or things like that. And then on the kind of more industrial side, there's also a huge variety of materials, not quite as rapid of growth on that side, just because there's a lot more going on with those machines and materials, so they can't really iterate quite as fast. And there's also a much higher, I think, threshold of capital that you need to have to be able to kind of play in that realm as a material developer. But let's just talk about like FDM, for example. So you have like Stratasys FDM machines. Just Stratus itself, I think, sells, it's got to be 20, maybe 30 materials. But then also a lot of companies are unlocking those machines now. So you have companies like 3DX Tech or there's all kinds of guys that have essentially hacked these machines, and now they're opening them up. So now they have their own versions of these materials, plus a whole bunch of other exciting things. So like FDM, there's at this point, there's got to be over 50 materials for FDM. I'm sure there's way more than that. Like MJF, like the kind of the newer technologies, FDM's been around since the 90s. MJF, I think, was like 2016 or 17. So with like MJF, we've got, let's see, nylon 12, 40% glass, Lubrizol TPU, BASF TPU. You have, I think it's Evonik TPA, Polypro, and I'm thinking I'm missing at least one in there, but that's all the ones off the top of my head. So smaller list, but and then you have 3D Systems, SLS machines. There's tons of materials for that. So it's a big question. It's like I could sit here for the rest of this and just rattle off materials, but the best thing I could advise is if you're wondering if a material is 3D printable, honestly, even what I do, you go on Google and you just type in this material 3D print. And Google does a great job of finding any little niche company that might have that material or something like it that is printable. So that's usually the first place to start if you're looking if a material is 3D printable.
And if you search for that, so say you find a material, that may help you determine what type of a machine or process you have to go to actually print that part.
Any material manufacturer that's worth worth working with is going to immediately tell you, oh, this is an FDM, or hey, this is an SL or a liquid photopolymer like an SLA or DLP, or oh, hey, this is a milled powder for an SLS or an MJF system. So yeah, they would and most of the time you can email them and be like, hey, I really like your material. Who's running it? And some of them have in-house service bureaus and additive manufacturing business units where they might be able to run it for you. Or a lot of times what they'll do is they say, hey, here's this additive manufacturer we work with quite a bit. We recommend you go talk to them.
Yeah. And if you're watching at home and you haven't checked it out, you can actually go to 3D Experience Marketplace. Paul, You're actually on 3D Experience Marketplace, right? Mm-hmm. So Absolutely. You can go to 3D Experience Marketplace and you can find manufacturers for specific materials there as well.
Yeah, that's a really good resource. There's a huge amount of materials called out on there, and it sends you directly to a manufacturer.
During our live stream session, we really focused on some of the differences between the different 3D printing technologies. I'll ask this again here. It was a question that was asked. Is MJF the same as SLA where the time doesn't increase if you include more parts? Is it based on the layers and height? So the question was, does MJF have, SLA is time based on number of layers and surface area. Is it the same for MJF?
No, the best analogy I can give you is if I said, hey Jeremy, why don't you come over to my house? I'm gonna have you paint a fence for me. And you show up and I go, okay, I can give you a paint marker and you can paint the fence with that, or I can give you a spray gun and you can paint the fence with that. Which one do you think you're going to be able to get it done faster with? Well, that paint marker represents a laser, and whether that's a laser on an SLA machine, a laser on an SLS machine, anywhere where you want that part, you have to essentially color in that region with the laser to either sinter or UV harden the resin. Whereas with like an MJF machine, you go across with a print carriage, and this is the same for like binder jetting. Polyjet is kind of like this too. You go across with that carriage, and it doesn't matter if there's one part or if there's 1,000 parts, because those inkjet heads are spraying the entire layer. So that layer takes 12.5 seconds roughly, whether it's one giant part or 1,000 little parts. Whereas if it was SLA or FDM or SLA FDM or SLS, it would vary widely on layer time, depending on how many parts and how much material you're sintering in that layer.
Now, when we look at the term SLA, there is also the DLP technology, but they'd be different there, right? They're doing the entire layer at once.
And that would be more of an entire layer at once. That's how like Carbon and Origin are able to show, Carbon and Origin really are able to show such impressive print speeds. Because they literally image an entire layer at a time. And so they're really able to crank up their printing speed. So yeah, absolutely same idea.
So Paul, this question is this is a unique question about 3D printer technology. Is there a way to print mixed materials? For example, a component, so this, I think of 3D printing and I think of more plastic-like material. So there's that question, but then also what about, can I mix metal into a 3D printing environment? Is there any way to really do that?
So not really. So, like, for example, with FDM machines, with those machines specifically, you can tell them to pause at a certain point in the build. So you could drop like bolts into the printed plastic, and then it will print over top of those bolts to encapsulate them inside your part. You can do stuff like that with FDM. You can't really do that with any other technology that I'm aware of. PolyJet has the ability. Remember, PolyJet's like a hybrid between like FDM motion with like SLA type part properties. With PolyJet, you can print both rigid and rubber at the same time, and so you can do like overmold, like you can simulate overmolds or like rigid areas with like soft, flexible areas. But again, that's a very much a prototype part. PolyJets really aren't up to end use environments because they're fragile and delicate and extremely expensive in most cases. So, you know, and then like MJF, SLS, you can't open those machines during a build to put anything in them. They're sealed environments. You can't crack into them. And there's no ability to print like a metal and a nylon at the same time. You know, there's a lot of really cool R&D going on right now in the 3D printing space. And I'm fairly sure in the next decade, someone's going to figure out how to do this. But for right now, there's really not anything out there that I'm aware of that allows you to really commingle like really different materials in the same build.
So, Paul, the next question, this question could be asked to the industry as a whole or your capabilities specific there at Forerunner 3D printing. And the question is what are your maximum printing capabilities?
So the maximum size here is a Fortis 900 FDM machine. And that is 36 inches by 24 inches by 36 inches. So that's our biggest printing envelope that we have. But in the industry, there's some really cool stuff going on. If you look up, if you Google Cincinnati BAM, I believe it's BAAM, the Cincinnati Machinery Company has some very large format FDM printers they're using for like wind turbine tooling and boat hull tooling. Thermwood Corporation, they also have some very, very large gantry style FDM 3D printers. And those, I mean, how long's your gantry? You know, if you think about how long a wind turbine blade is, you know, I've seen some really cool stuff where they're doing giant sections of tooling. You know, I think the biggest one I saw was like 15 feet of gantry travel. I think it was about 12 feet wide, and I think the Z was in like the 8 or 9 foot range. So very, very large format. But on those larger format machines, they're laying down very heavy layers. So the part isn't done after it's printed. They actually swap the head out, come back with a milling head on the exact same gantry, and then they clean up machine all those surfaces to give you a nice, clean surface that you can use to do layup for composites and things like that.
This is an interesting question I have for you, Paul. It says, I'm curious, does the material work well with adhesive liquids?
Yes, as it does. So, you know, you think about like our printers are all different sizes, but like, you know, something like our MJF machine is only, you know, 15 by 11.5 by 15 tall. Well, I mean, we'll sometimes do huge assemblies that have to be, you know, printed, but we obviously can't print them as a single piece. So we'll go through and we'll put glue joints in there. And specifically, we found there is a product on the market from Loctite, and I'm desperately trying to get to my notes here. Let me just look this up a second. There is a product from Loctite that we've done. We're actually going to be releasing a whole testing video of bonding different types of 3D printed parts. So like an FDM part to an MJF part, or a nylon MJF part to a nylon or to an MJF TPU part. And we want to see how this glue holds up, like what kind of pull strength can we get from different materials with the same glue. So let me I'm almost to the folder, and then I will be able to actually give you a name here.
Well, you're looking for that folder, Paul. You know, back in the day, you're talking about adhering, you know, different 3D printed components together. When you deal with SLA, isn't it like one of the tricks you can actually use that resin and use a portable like light to actually fuse it together as well?
Absolutely. So the stuff we use is Loctite 3D printing universal bonder. And so that's the stuff we've had the most success with, and we'll be releasing some videos on LinkedIn here probably the next couple of weeks showing some really interesting R&D we've been doing around that. But yes, we also, with our SLA machine, we do giant parts with that all the time, and you can go and essentially scoop some resin out of the vat, or they sell in patching kits and stuff like that. We use both, but essentially you sit there, slide your parts together, and because the resin is UV reactive, we actually use I think it's called an EFOS. They use it to put fake nails onto your real nails with like a UV light. So essentially it's a long fiber optic, and you turn it on, it kicks out a super high intensity UV light, and you can go along and spot cure that resin to create a seam to glue your parts together, or in this case, bond them together, because it's the same material that they're printed out of.
I still find it quite fascinating that Loctite generated a specific adhesive for 3D printing. It's called out for 3D printing specifically.
Well, it's actually just a rebrand of one of their current products, but they did some testing to make sure it works. So yeah, I don't know the actual number for it, but if you look up Loctite 3D printing universal bonder, that's the stuff that I recommend for putting parts together. And it works. So far, it's worked on every substrate we've put it on.
All right. And if people want to go watch the testing that you do on your LinkedIn page, can you tell us really, just go to search Forerunner 3D printing on LinkedIn?
Yeah, best way to find us on LinkedIn is to probably just look me up, Paul DeWys, so Paul DeWys on LinkedIn, or Forerunner 3D printing on LinkedIn, and you'll be able to kind of get to me through that through our company page. I post everything through my personal profile, so if you want to see that, definitely connect with me directly on LinkedIn, and you'll always see the latest stuff that we're posting. Also, our website, forerunner3d.com. We've got tons and tons of pages built out on there with all of our R&D videos. So everything winds up on there and on LinkedIn eventually.
Paul, the next question we talked a little bit on the live stream about, I'm going to ask you this here again, just in case people want to see the answer again. Are there strengthening coatings or sprays that you can use on parts after 3D printing them?
So I believe my answer the last time was not specifically, but after I thought about that a little bit more, there is one thing you can do. There are companies out there that apply metal plating to 3D printed parts. And so there's a couple of them out there that'll do this. And I have definitely seen some people take like FDM or SLA parts that are maybe a little bit more fragile and send them out and get, 5,000ths of nickel put down on top of the part. And it does actually greatly improve the strength of the part because it's a metal plating. So that is technically, I guess, a coating that you could apply. But get ready to pay some cash for that. It is a fairly expensive process, so it's not something that we do all the time. But we have done it in the past when we had an SLA part that needed some extra strength, or if we were printing a part that needed to be conductive. We've also had that before, where we're using prototyping press transfer fingers, and we need them to be conductive to know that the press wasn't dropping parts. So it can be done, and that would be my new answer now that I've thought about it for a minute.
All right. What are some of the 3D materials that can withstand higher temperatures, and how hot can some of these materials withstand?
So I'm going to give myself a shameless plug, and I will answer this question. But if you go to forerunner3d.com, and once you get there, if you go to I believe it's the 3D printing machines and material button at the top, there's a list of all of our different machines, and below each of those is a drop-down list that says 3D printed materials available. And if you go on here, there is a massive variety of materials that we support and all their material data sheets. So off the top of my head, I can tell you that like PA12 for the MJF machine, that's good up to 369 degrees Fahrenheit. Altem 1010 for the FDM machine, I believe, is our most thermally stable, and I'm actually going to look at it right now. I'm actually on my own website looking. Let's see here. So Altem is good. It is a heat deflection temperature of 421 degrees Fahrenheit. So that's not necessarily the glass transition temperature. That's where it starts to soften to the point where you can start to move it around. So yeah, I mean, Altem is going to be right up there at the top. Peak, PEEK, I believe is pretty good as far as thermal resistance goes. But typically, when someone comes to me with like a really high temperature application, I'm looking at Altem 1010 or Altem 9085 for the Stratasys FDM machines.
This is a question, I think, Paul, that goes back. They're asking a question. Did we cover it in the live session? Did you mention the temperature range for the HP printer? Maybe what those materials can handle. Again, we've kind of talked about this already. Is this where you'd kind of recommend them to go back to your website and look that up?
Yeah, so again, I would recommend 4runner3d.com, and then at the very top, there's a button called 3D Printing Machines and Materials, and inside of there's the HP Jet Fusion, and you hit the drop-down titled 3D Printed Materials Available, and there's your technical data sheets for all of those right there. But I can tell you that the material that we run the most of, which is also the hottest, is PA12, and the material I think is actually its melting point. Let's see if it's actually in this data sheet. Yeah, they don't have the glass transition temperature in here. Oh wait, here we go. Powder melting point. So that is that 369 degrees Fahrenheit. So roughly that printer's probably running somewhere between 350 and 400 degrees when it's printing parts. Now they have a newer version of the machine. It's called a HP MJF 5200, and that can do higher temperature materials like polypropylene. I don't know what that one actually runs at, but I know it can do higher temperature materials than the 4200s that we run here.
Paul, it's interesting you're talking about a lot of these different materials. One of the questions we have is, what does the term ABS mean in terms of materials for 3D printing? Are we talking about the same ABS plastics we would use in a plastic injection molding environment, or is there a difference in the material?
So it is ABS. So like if you're running an FDM machine and you're printing with ABS, yes, it is similar to the ABS that you would be using in an injection mold machine. Now, the thing to keep in mind is there's different grades of ABS. There's different fill materials put into ABS. So it's not like there's just one ABS and you run it in 3D printers and you run it in injection mold presses. There's many, many grades and formulations of ABS and fillers and things like that. So, on a basic level, yes, they are the same, but you should always consult the technical data sheets for like 3D printed materials, because they're going to give you tensile strength, they're going to give you elongation at break, they're going to give you heat resistance, and you could get those exact same technical data sheets for an injection molding version of ABS, and you can actually compare them one-to-one. And that's what I do with a lot of my customers is, help them compare materials. Here's what we have available with 3D printing. Here's what you want for injection molding. Are they close enough, or do we need to look for something else for 3D printing?
The next question is, are any of the technologies that we talked about relevant for printing any flexible polypropylene-like materials?
So yes, so there is a polypropylene material available out there. I know it's available on the MJF platform. I think it may be available on SLS printers as well. Flexibility. If you're looking for like living hinges or snaps and things like that, that'll absolutely work in a polypro. It always seems to me like printed polypro isn't nearly as flexible as what you find with an injection molded version. That's just a personal opinion. I'm sure there's other people out there that would disagree with me on that, but every time I've tried to use it for a flexible application, it always seems a little bit stiffer than what I expect it to be. So, I mean, what we do is like, let's say you have a snap feature or, something like that. We tend to go with thinner walls in order to make those really, really flexible in nylon. Polypro can be very, very challenging to print in, especially for big parts. They tend to really want to warp and twist in the cooling process. So we tend to actually stick to more of the nylons and stuff like that if we're trying to do like checkout snap features, or SLAs are great if you're trying to check, plastic snaps and things like that. Our next material is tuned to perform like ABS. Even though it's not ABS, they tune the mechanical properties to be somewhat similar to them, so you can see how those snaps and things like that are going to work, even though it's not actually the end material you'd be using. So yeah, there is definitely polypropylene available out there should you want to go that route, though.
This is a good question, Paul. Can 3D printing, can you make parts out of metal is basically the sum of the question. And that's something we've touched on. There's other, I'll let you go ahead and answer this because I think it goes beyond metal even here.
Yeah. So yes, short answer, yes, absolutely. Metal printing is something that kind of came around. I think it really started to be commercialized in the mid to late 90s. So it's a little bit behind where polymers are at in just a time in existence. But there's companies like SLM. It used to be Concept Laser. It got bought by GE. I'm not sure what it's called. These guys or what these guys are calling it these days. There's Desktop Metal, Velo 3D, I believe. And that's the cool thing is a lot of the patents are starting to come to the end of their life or expire. So there's a ton of little startup companies coming into the metal printing side of things. And there's kind of like we'll call it two main fields of this. There's the powder bed guys like Desktop Metal, or like HP has their metal jet technology that'll someday maybe come to market. And that is essentially they print with a metal powder and they spray basically a glue binder onto it layer by layer. And when you pull out the part, it's in a green state. So you could break it apart in your hands. But if you put it into a sintering oven and you take and sinter that part, it shrinks like, I don't know, 20 or 30%. And then now it's burned all the binder out of it. All that metal has hopefully fused together. And now you have a solid metal part. So that's, the kind of the powder bed binder jetting side of things. And then the other side is the laser-based system. So this would be like EOS, SLM, GE's additive business. And so basically they lay down a layer of powder, and then they have high-intensity lasers that come down and actually locally melt the powder with a laser beam, and they do that layer by layer, and essentially they're melting that powder to the particles next to them and welding those particles to the layer below them as well. And there's some other hybrids and different things in there too, but we're going to just leave it in those two main categories. If you're interested in metal printing, there's a ton of really cool stuff on YouTube. If you just kind of YouTube search around and look up metal 3D printing, there's tons of people who have much more experience in it than I do. We don't do any metal printing here. We distribute for a metal printing company, so I do some sales engineering for them. But it's kind of a completely different beast from what we do with the polymer side of things. So really cool stuff, though. They're doing some really neat end use parts with metal right now.
And, we'd be remiss, one of our partners at 3D Experience World every year, Desktop Metal, you mentioned them, they're there every year. But you can also kind of like go down kind of between that polymers and metals realm. I think maybe I'm being presumptive in the way I'm describing this, but we also have the carbon printing that you're doing with, boy, I can't think of the name of the company right now off the top of my head. Markforged, yes. Yes.
I should have given them a shout out. They're a great SolidWorks supporter. Markforged, they're not doing the powder glue together type scheme. What they're doing is they have an FDM machine, and they're extruding a filament that is both the binder and metal particles in the filament, and then layer by layer building those up. Then they take that essentially FDM part and fire it in an oven and sinter it, and then you're left with your metal part. So they're kind of more on the binder jetting side of things, although it's not binder jetting.
Yeah, two very cool technologies. I always encourage, if you ever get the opportunity, go to, next year we're going to have a hybrid event. Go to 3D Experience World next year, and you could see both of those technologies. Very cool stuff.
Absolutely.
Another material question for you here, Paul. Is it possible to print stainless steel? We talked about some of the metal printing technology.
Absolutely. In stainless steel, I think you can print 17.4 and I think 316. I'm not 100% sure on that one, but I know there's a variety of stainlesses available. I believe in the past we've done some 17.4 stainless parts before with one of our vendors. And so, yeah, stainless is absolutely an option. It's used obviously a ton in medical device, and medical device is a huge user of metal printed parts.
We briefly answered this question a little bit ago. It had to do with metal printing. What about Markforged as a more cost-effective metal printing solution?
Yeah, so I'll be honest, we don't run Markforged equipment here, so I'm not going to go too deep into this because, quite frankly, I just don't know enough about it. What I can say is the machines, the Markforged machines, are way cheaper than what you would pay for like a laser-based system, like a powder bed laser system from EOS or SLM. They work differently than those. With a Markforged system, you print the part, and then once it's printed, you have to put it into an oven and actually sinter the part to burn all that binder out of there and actually make it a true metal part. I can't really speak to the economics around a Markforged versus making parts other ways, but I can tell you that it's a definitely lower cost way to get into the metal printing side of the business.
All right, Paul, the next question we have is, do you have any specific ways you compare the mechanical properties of 3D printed versus machine parts?
I mean, so we've done a fair amount of like pull testing and brake testing and stuff like that, where we will actually mount parts onto a pull tester and we'll put a camera on it and we'll just pull on it until it breaks and record what the force was in pounds of when it actually failed. Quite honestly, we've never done any heads up testing to like getting a part machined and then printing an identical version of the part and then breaking both of them to see where they come out against each other. We haven't really had a need to do that yet. So, that would be something that I think would be, you'd want to, if you want to try to establish those numbers, that would be the way we would go about doing it. I think, the simulation software that's out there, like the SolidWorks simulation software, is really, really great for metal parts. And if you have the nonlinear package, which is really cool, but also quite pricey, if you have that nonlinear package, you can do some cool stuff with like injection molded parts. But additive is not injection molding. There's layers in there, so you can't run like a nonlinear simulation on like an ABS part and then expect those results to match like an FDM version of an ABS part, because your X and Y and Z, X and Y probably have similar strength characteristics, but Z, the layer the direction that your layers are in, will be significantly weaker in most cases. So you got to be a little careful with FDM, because I'm looking forward to the day where the wizards at SolidWorks will come out with a FEA software that will allow us to simulate that. But that's still something that I think is in R&D at this point. So we have to be a lot more physical with like actually breaking parts in the real world to compare one to the other.
Paul, we have another interesting question on 3D printing technology and where it might go in the future. I'd love your opinion on this. Thoughts on true 3D printing with non-planar layers? Do you think it is something that will eventually be a thing? Some of the potential advantages as it comes to part strength in the y-axis.
I've seen some really cool R&D stuff coming out of some of the college labs and stuff like that. I really haven't looked into this too deeply. But some of the stuff I've seen, it has to do with, like 6-axis robot arms, kind of like we were talking about earlier with the relativity space guys. Yeah, I mean, I think that, there's some cool stuff. I haven't seen anything that's really commercially viable so far. I've seen a lot of cool technology demonstrators, but I haven't seen anything that really looks ready for prime time. But you know what, like, a lot of stuff I'm doing right now was a technology demonstrator 5 or 6 years ago, and now we're using it. So I'm definitely keeping an eye on it. I'm curious to see where they can take it, and if they can get it to a point where it's robust enough and easily used enough where we could bring it and commercialize it into a service bureau like where we're at right now. Haven't seen that so far, but actively keeping an eye on it because I think it's only a matter of time till they figure it out and we get to see, like he was talking about, the isotropic benefits of going in all three directions instead of just planar layers.
Paul, the next question is a pretty good one. When we look at everything going on in the world around us here, what do you think some of the challenges of 3D printing in space would be?
Okay, well, I keep hearing about this. I've had a couple people actually email me in the last year, and this has been something that's been brought up. I hear about microgravity and zero gravity fabrication. I don't really know much about it. I think they just brought a 3D printer up to the International Space Station to do some kind of experimental stuff up there. I'll be honest, I haven't really looked into it. It sounds a little pie in the sky to me. I mean, I know what it costs to move stuff up into space right now, and obviously SpaceX and Blue Origin are trying to get that cost down. But I mean, we're talking very, very, very expensive to get raw materials up into space. So I think you'd have to find a way to fabricate them up there. So I mean, maybe if Elon can get his asteroid harvesting business going, and we can have raw materials in orbit. Hey man, I love cool stuff, and if we could put a Forerunner location on the moon, I'd be all about it. But I don't know. I probably am not the right person to really speak deeply on this, but I think it's cool, and I'd love to see it come to fruition.
This is a cool question, and I like this question because I can point back to another SolidWorks Live episode we did back the month before yours, where we talked about Delmia, and it's would you recommend using a robot with 6-axis to make a 3D printer?
Yes. Google Relativity Space, and these guys, I believe, yes. So what these guys have done is they have a 6-axis robot with some kind of crazy welding head on it. And they are welding these giant aerospace parts, specifically, I think, a lot of fuel tanks for the space industry. And it is a 6-axis robot, and they are using it as a 3D printer. So, yes, to whoever asked this question, you're thinking in a very, very smart direction. And these guys, they're doing it right now. Their website is fascinating. Their YouTube channel is incredible. I highly recommend going and checking out their stuff. They're going to give you a much better answer than I ever could. So relativityspace.com.
Paul, the next question is, can we use 3D printed ABS directly as a motorcycle panel? Can they perform good mechanically? And I think this question isn't, let's not just ask this question about a motorcycle panel. Let's talk about something in your walkthrough video. Maybe it's the steering wheel of a car, or maybe the arms of this chair. How are the mechanical properties going to compare to the real life? But we'll answer his direct question on the motorcycle panel.
Sure. So to answer his direct question on the motorcycle panel, I would say, is this a nice Sunday driver where you're going 45 miles an hour through your down country lanes? Or is this a Ducati where you're doing the Isle of Man TT and you're going airborne at 130 miles an hour? I would say if it's the Sunday driver, you probably could get an FDM printed part to work for a panel, as long as it's not structural. If this is a frame component, absolutely not. But if it's like a fairing, or if it's a windshield, or not windshield, but shielding for aerodynamics on the bike, I bet that could work. But I will tell you this: there's a company, they make a material, I think it's called Windform, I believe is the brand name of the material. CRP or CPR, that's I believe the American division of their company. It's out of Italy, and they developed this carbon fiber, I think it's carbon fiber loaded nylon for SLS machines, and they developed it specifically for high speed bike racing and Formula One. And this stuff is obscenely expensive. I've quoted one job ever in it. And it was, I looked at the quote and I said, there's no way anyone will ever pay this. But, Formula One, I mean, those guys, they have hundreds of millions of dollars in their budget. And if they can squeeze out a couple more mile per hour, they don't care what the cost is. So if you look up Windform SLS material, there's some pretty cool superbike stuff out there that they've done. And it's directly on the bike. And I mean, this is the crazy, European superbike guys. So yes, you can find that material, and you can find behind that machine. And it's all about, what am I doing and what machine and material go best with it. And it doesn't just apply to motorcycle parts. That applies to anything you're working on. So, we've got customers in heavy agriculture where, we're building parts that are going onto planters and things like that. And these are going to be drenched in UV light. They're going to be, fixed with a hammer. If they're broke, the answer is always a hammer. And if that hammer doesn't work, get a bigger hammer. So, something like that, it's going to be like a nylon 12 coming off an SLS or an MJF machine. We have medical device customers where they're testing, they're building, hundreds of prototype CPR like bags, like where you squeeze the bag and it does CPR for the patient. We got a customer that we built hundreds of these little check valves for, and they were using those as pre-production for their sales team to go out and sell this product while they're still cutting tools. Well, there it's like in a very sterile, temperature controlled, no UV light, and there's a lot of fine detail. So we wanted to use SLS for that because it would be better suited. So, and if you took and flipped those and you went MJF to the medical device and you went SLA to the agriculture guy, it wouldn't work at all for either one. So it's all about knowing what you're trying to do and then finding the material and then working backwards to the machine that actually runs it.
We've kind of mentioned this a couple times today, and I think we talked about it during the live stream, and that's, understanding the right 3D printing process for the application at hand and the materials involved there. So there's no one answer for all of these things. Clearly, you want to work with somebody like yourself, Paul, to kind of determine, if you don't have that answer yourself, what the right answer is there.
And I will be the first one to tell you, additive is not always the answer. Sometimes it is, hey, go get this machined. Hey, go get this cast. Let's get it fabricated. Additive is one more tool in your toolbox. It is not the solution to every one of your problems.
So, Paul, would you suggest using a 3D printed product as a final product in limited production? For example, a PLA material for lightening up products.
Yeah, I mean, you can absolutely, yes, you can absolutely do that. I would say it really depends on the product. So, like I talked about when we were doing our SolidWorks live conversation, I have a side business with some partners where we develop our own products and then commercialize them. And some of those products are 3D printed. Actually, funny enough, I actually have one of our products sitting on my desk because we're going through some engineering changes right now. This is a mount. It's called a stable mount, and it goes onto a compound bow in order to hold like a GoPro camera. And so this product originally, we started out FDM 3D printing it on our MakerBot all the way back in the day when we were just getting into this. And then over the years, we transitioned it to our MJF printer in nylon, and we actually sell that part on Amazon as a printed component, not as a injection molded or anything like that. And I mean, we've sold thousands and thousands of those things, and it's printed. It's a printed part, and had really good luck. We've had a few of them get sent back because they broke, but generally it's because the guy drops his bow out of the tree stand, and he's got usually bigger problems than a broken stable mount. But yeah, I mean, that's an end use part that is printed and sold to the general public. So you can absolutely do it. But, let's say that you were doing, for example, I've had people come to me before and want to do custom, or not custom, but do kind of very unique brake levers for like mountain bikes and stuff like that. And I look at something like that and go, man, if that brake lever breaks in your hand and all of a sudden you're going down a mountain without brakes on a mountain bike, that seems like it could be a little dangerous. So, I always sit back and go like, okay, and I think, and this isn't just for additive, this would be for any manufacturing process, but I think you have to go like, is this a life support or a human safety related product? And if it is, I think you should think very long and hard about any process you would use to manufacture it. But in this case, specifically additive. But if it's a mount to hold a GoPro on your bow, there's no real risk of you getting hurt or killed because that thing fails. So I would encourage people to think about that when they're thinking about using an end use part is, what is your application? How is it being used? And yes, it can absolutely work, but you got to come at it with the right mindset and being kind of intellectually honest with what you're trying to do with the part.
Can you give some examples of products that have come from SLA specifically?
Yeah, so one of my favorite examples is if you go on to YouTube and you search for Invisalign SLA 3D printing. This was the first killer use case for 3D printing in end part manufacturing. So Invisalign are those clear retainers that you can get, or clear aligners that you can get, as opposed to like metal braces. And if you think about it, there's no two sets of teeth in the world that are the same. They're all different. And then if you think about it, you start with your teeth in one position, and over all of these aligners, they shift them to a different position. So even there, every single aligner is different. So we're talking millions and millions, probably billions across the history of Invisalign, of all these different molds that they need to make. And so if you Google that on YouTube, you can find a video from the early 2000s where they actually did like a full video walkthrough of their manufacturing process. And there is just a room full of SLA 5000s printing thousands, probably tens of thousands of aligners a day, and then how they go through their manufacturing process. That would be like the first really like killer use case for an SLA 3D printer for end use parts. Even though it's not the parts that are going into your mouth, it's the molds that they go over top of. That's always one of my favorite examples. And then there's lots of other stuff that have kind of come since then, but that's the one that probably most people would be able to relate to.
All right, very cool. I think I'm familiar with those. I've seen them myself.
Yep.
Kind of game changing. I wish they had those when I was a kid.
Oh, me and you both, buddy.
So, Paul, we touched on this question during the live stream in a decent amount of depth, but I will ask this question again here. Do you think additive manufacturing can someday replace CNC machining in traditional subtractive manufacturing methods?
Not in our lifetime. Yeah, maybe someday in some distant future, maybe anything's possible, right? Like, but for here and now, no, because I just don't think that, additive has limitations around accuracy, around surface finish, around speed in some situations.
What about cost? I mean, that's like right? Like that's always something to consider.
Absolutely.
With volume comes difference in cost, right?
You nailed it. So let's say that you were doing a large aluminum plate. Maybe it's 3 foot wide and 2 foot deep, and you're pounding 40 or 50 holes into it, like a tabletop for a piece of automated equipment, or a giant aerospace structure or something like that. You just would never be able to, in my mind, economically compete with what a CNC machine could do in that same environment. Maybe someday for aerospace structures, but even there, you have such huge quality and safety ramifications of something like that. CNC machining is just really, really good at that type of stuff. Big parts. Right now, additive really struggles with big parts from a cost basis. And so you would have to have a very, very unique situation where additive would make more sense than a traditionally machined or fabricated part in something that big. So no, I think they're very much complementary technologies. I think what you will see is, I think you'll see every machine shop, out there in the next 15 or 20 years are going to have an additive department. I could see that, but I don't see anyone saying, "Oh, get all these stupid CNC machines out of here. I'm getting 3D printers." I don't think that's going to happen in our lifetime.
That's probably the same reason we have people, welding tubes together as opposed to machining everything out of one giant piece of billet, right? It's the same reason. Different manufacturing processes serve different needs based on scale and scope and all sorts of other parameters that define that.
Yeah, I think we're a long ways away from that, like Star Trek, like it just formulates it and it just spits it out. Like I think we're very, very long ways away from that. I think that additive is just another tool.
Do you think every machine shop out there should invest in their own 3D printing, 3D printers for little parts? Would there be a benefit? How expensive would it be to set up? Or should they just go to guys like you to have these parts made?
This is going to sound like I'm shamelessly plugging a SolidWorks partner, but honestly, this is the answer I give to everyone. Any shop that wants to get into additive should go buy a Markforged. For $5,000, you can get up and running with the base level Markforged machine, and you will learn so much with that machine. And pretty much anyone can go to their boss and figure out a way to cost justify, a $5,000 investment. And there's so much that those machines are so capable for their price point. It's just insane. Yeah, I mean, I think any machine shop, any machine builder, any R&D business, anyone, building stuff, I really, really think should have some form of 3D printing. And it doesn't have to be a Markforged. It could be an Ultimaker. It could be a MakerBot method or whatever. It could be a Rise. There's lots of machines out there. I personally find the Markforges to be the most capable in my customer base. But yeah, I think everyone, should between $5,000 and $10,000 be able to invest in some form of 3D printer. And what you're going to find pretty quickly is you can do some really, really cool stuff, but with the Markforged specifically, or any FDM machine specifically, you're limited on speed and you're limited on throughput. So what you'll find out is pretty soon you've got a whole bunch of jobs stacked up, and you got one poor little Markforged machine running 24 hours a day, and you're like, I am never going to get through all this work. And that is when you pick up the phone and you call someone like me and you go, hey, man, we need to push some volume through this thing. My boss loves additive all of a sudden. We're showing him all this cool stuff we're doing. We're driving down prices, or our costs and things like that. Then you come and form a relationship with someone like me, and, we can be, the big engine behind you to say, okay, we need to get 35 nesting details done in the next week and a half. Okay, we can push that kind of volume through our equipment. But by having your own in-house, you're going to learn a lot of these lessons, and you're going to be able to prototype stuff really, really cheap in-house before you come to someone like me. And then now you're spending, more money, and oh shoot, maybe the first version didn't work. Well, if you could have done that on your own machine in-house, you would have confidence in your design, and then you could say, all right, Paul, I need 100 of these, so get it going, and not, hey, I need one of these, and then a week goes by, and hey, that didn't quite work. Here's another one, and another week goes by. So that's what I encourage people is think about it from a hybrid approach. A lot of people have a Bridgeport manual mill sitting in the back of the tool room, and they'll get something kind of put together, and once they're happy with it, then they call the high-end machine shop down the street and go, hey man, throw this on your Mori or your Haas and make me this really nice high-end part with confidence that it's going to work. I think you should look at additive the same way.
Great answers there. I love it. I think it's really good. People invest in the technology and then work with partners to fulfill bigger manufacturing needs as they move forward there.
And one more thought. I mean, and that's the stepping stone to get your boss to pull the trigger on a bigger machine. If you can show him a positive ROI in that little machine, he's going to be a lot more likely to give you the budget to go buy a bigger one of your own.
Paul, we're going to go back to a manufacturing specific question. We've kind of dabbled with this throughout these questions. And the question is why would somebody use an FDM printing process over casting when the cost of casting is so inexpensive? And I'm going to throw this out here because I'm sure a similar question will come up. What about injection molded parts here as well? You want to go into some of the details of why would I use a 3D printing process over these?
Yeah. So, look at it this way. You have a tooling cost with injection molding or with most metal casting operations. There's always going to be some form of tooling. And if it's a simple part, that tooling cost might not be terribly excessive. But if it's a complex part, I mean, I've seen injection molds all the way up to close to $1 million for really, really complex tools with lots of action in them or lots of moving pieces inside of them. And so, you may be bringing a new product to market, and maybe you're going, boy, I'm about to drop $100,000 on an injection mold, and I don't really know what the market demand for this product is going to be. What happens if I spend $100,000 and then maybe another 15 grand in getting parts produced and packaged and in my warehouse, and then no one buys them? Well, now I'm out a big pile of money, and I have an injection mold sitting here that I can't do anything with. And another way to go about that would be, hey, let me look and see if there's a 3D printing technology that could maybe allow me to print 1,000 of my first parts. And then I can go to market with those. And I will also say urethane casting is another method that can be used to do this with even better surface finishes and lower. And there is some tooling expense with cast urethane, but not even close to what there is for injection molding. So, whether it's 3D printing or cast urethane, you could maybe do your first 1,000 parts that way. And yeah, your per part cost is going to be way higher than what it would be coming out of that injection mold. But your risk, your capital risk of saying, holy smokes, I spent $115,000 and no one bought my product. You could probably cut that down to an eighth of that number and go, oh wow, no one bought my product. Well, at least I'm only out, 10 or 20 grand instead of, $100,000 plus. Also, it can help you get to market faster. Let's say you've got an innovative idea, but there's a competitor that's nipping at your heels, and you really want to be the first one to market. Like maybe you're doing like a Kickstarter campaign or something where there's multiple people competing on an idea. Additive could allow you to get to market a couple weeks earlier than traditional tooling would. And so, but in both cases, what I always tell people is, yeah, you're going to pay more for those parts, and maybe you're going to have to sell them at cost. Maybe you won't make any money on that first 1,000, but you validate the market, and now you spend $100,000 on that injection mold with confidence, and then that cost of that 3D printed part goes from, let's just say, $35 a piece to $2.50 a piece. And all that goes directly into your pocket to pay off that mold and eventually turn into profit down the road. So, yeah, there are times where you just go directly to molding, but, especially for smaller companies, startup companies, I think injection molding and urethane are a great way to validate your market before you go spend the big bucks.
All right, Paul, the next question covers a topic I think we briefly touched on during the live stream itself, and it was, how do you control the surface finish of 3D printed parts?
Boy, that's another big question because it all depends on what type of machine you're using. So, for example, if we're using like a FDM or SLA, where you have solid supports or potentially wash away supports in the case of an FDM, but even in both of those cases, your downward faces are always going to be rougher than your sidewalls or your top face. So if you have a really critical surface, don't point that down in your build envelope if you're doing SLA or MJ or FDM. Now, you could also look at like SLS or MJF, which are powder bed machines, or Polyjet, which is like if FDM and SLA had a baby, essentially. It's a gantry style print heads, but it's spraying out essentially a form, and then it's filling it with SLA resin and then curing it. And so in that case, again, your downward faces will have a slightly worse finish than maybe your upward faces, but that's way better than what you'd get with FDM or SLA. So in the machine, that can make a big difference, but then even post-processing can make a huge difference. So let's say you did do an SLA, like we print SLAs every day here, and on the downward faces, we have what we call stubble, which is all these little bits of plastic hanging off the bottom because we had to break all that support off of there. Well, now all we do is go through with a little sandpaper and just sand it off, and maybe go through, a couple stages of sanding, progressively finer and finer grit, and eventually you sand it completely off and you don't even know it was there. Now we have some customers that they need a complete Class A part, so we'll sand the entire part all the way around, remove all the layer lines, prime it, and then send it to them, and then they might hit it with automotive paint. They might send it out for plating, for chrome plating or something like that. And when it comes back, it looks like a final part. You wouldn't know it was 3D printed. Now, anytime you're doing that, you're driving your part costs way higher, because I got a craftsman sitting at a bench downstairs, and for every minute he's touching that part working on it, the cost just keeps ratcheting up and up and up. So a lot of times what our customers will do is, like, we start out with like engineering models. So it's like quick, dirty, fast. I don't really care what it looks like, just get it to me as cheap as possible. And then by the time they're getting to the end of their development cycle, they're like, all right, now I got to go show investors, board of directors, marketing team, salespeople, customers. Now I want to spend the money on a really nicely finished model. And so all the ones before that were really cheap. They maybe didn't look the best, but they were functional and they could check what they needed to. The last one, we really make it look primo, and now they can bring it to those people and take the project to the next stage.
The next question we have are, what are some of this is an interesting question. It might get a little in the weeds for you here, Paul. It says, what are some of the parameters we should keep in mind while adjusting supports and rafts in SLA?
Boy, This is one we could definitely get in the weeds on. So, with supports in SLA, you really got to think about like making sure that and it really depends on the SLA machine, but I'm going to talk specifically to our style, which is a 3D Systems SLA 5000. So you have a recoater that's constantly going back and forth, spreading fresh resin over top of your part every time it drops down into the build chamber. And so a big thing is like if you have a really fine feature that's kind of out by itself, and it's going to print over here, and the bulk of your parts over there, and eventually the layers are going to come together up there. You want to make sure that this little island out here has a ton of big, broad support on the base. It's almost like building a skyscraper, right? If you're going to build a skyscraper, you're going to drive pilings deep down. You're going to spread that base out, have a big mass of concrete. You can think of that the same way, because that recoater is going to be going back and forth over top of there. You don't want that to just break off, and now this whole side of your part failed. So that's something that I'm always thinking about. And then also like tooth geometries. So whether I'm doing like a fine tooth where and when I say tooth, it's like the tooth that actually connects up to the bottom of your part that actually rips away when you're done printing, using a fine tooth versus a coarse tooth. And those have benefits and drawbacks either way. But, they can also make a big impact on post-processing. A fine tooth leaves way less stubble behind than a coarse tooth. So I'm always thinking like, is this an engineering model? Is this a finished model? Kind of back to the last question we had there about surface finish on your downward faces. But I'm always a fan of like the broader I can make supports, the better off I'm going to be. And I'd rather spend a little bit more time at the bench doing some model making and sanding versus getting halfway through a 25-hour build and having it blow up in the machine and having to start over. So I always err on the caution of more supports versus less.
All right. Paul, the next question is about some specific equipment. We're asked, I've been using an Ultimaker Cura 3. I had a problem with the draft and thermal expansion of the product. What should be the allowances? And along with that, we actually, talking with one of our producers for this show, they have a 3D Walks Cindo printer, and they were kind of asking the same question too. Care to answer this one?
Yeah. Honestly, with especially with desktop 3D printing, there's no one answer that covers every machine. What I would tell people to do is, I can't sit here and give you a straight answer because everyone's environment is different. Are you using an enclosed chamber? Is that chamber heated? Are you running PLA? Are you running ABS? Are you running some other crazy material? So there's too many variables for me to be able to say like, oh, it's this, and this, and you're done. What I would recommend is what we do here, which is, create a design of experiment. So, take and start out with, a 1/4-inch cube in the middle of your build platform, and then just bump that cube up, maybe a 1/4-inch or a 1/2 inch in size, and keep your infill and your raft settings exactly the same. And then, okay, I know that this cube that it should be, 1/4-inch by 1/4-inch by 1/4-inch. Then I take my calipers and I measure it and I go, oh, it's actually, maybe 10 thousandths short in the Z, but it's 25 thousandths big in the X and Y. And now you do that all the way up till you essentially have filled your build chamber. And yes, I know that's a lot of time and a lot of material. I'm very aware of that. But that's what we do here to develop these kind of like curves that essentially here's the curve of what it should be, and then here's what the curve is of what it actually comes out to. And that can help to guide you in knowing like, oh, my part is roughly 6 inches by 6 inches. Well, I better plan on it having this much variation versus, oh, my part is 1 inch by 1 inch. Okay, now I only need to accommodate for this much variation. But I will say environmental factors play a role here. So if your environment that the machine is running in is not consistent, your parts will probably not be consistent on the machine either. Even here, we have these temperature controlled, humidity controlled labs, and even here sometimes we have builds that just go crazy and you just can't figure out why. We had one yesterday where we had a whole batch of parts that were ruined, and we're sitting here scratching our heads going like, what changed? We've run this job 20 times before this and they've always come out fine, same orientation, same build settings, but we scrapped an entire build. And sometimes you just get screwed. Sometimes you're just going to have those bad builds. So look at the data across an average. Don't look at individual points of data, because I think an average is a truer representation than individual data points.
So say you create all these plot curves. You've done it in X, you've done it in Y, and you've done it in Z. Would you then recommend, like say in SolidWorks, using the scale tool? And so say you're off by a 0.5% in Z and 1% in Y and maybe no percent in X. Would you then like use that tool before like outputting
Absolutely.
that?
We've done that. We've done that exact thing before where, we've got a really complicated piece of nesting with a really precise fit, and we print it the first time and it comes out, 50,000 small in the X direction. You don't want to go through and have to redo all that surfacing and everything like that. So we'll round trip it. We'll save it out as a parasolid. We'll run it back into SolidWorks. Now it's just a dumb body so we don't blow up a whole tree worth of work. And then you can sit there and use that scale tool to scale it in the direction that you need. So yeah, scale tool in SolidWorks would absolutely help with that.
So, Paul, the next question I have is a fairly long question. It says, additive manufacturing is a great thing, but not exactly new. I'm curious what capabilities SolidWorks provides me to actually design products in a way that let me benefit from additive, e.g., generative design or topology optimization. What are some of the design technologies you've seen, Paul, that are kind of focused on this additive manufacturing technology?
Well, I think generative design is really where it's at right now. SolidWorks has a generative design, package or module or whatever. I think it's inside a simulation, if I remember correctly.
We call it topology optimization there. We do have generative design in 3D Creator, which is X design as well. It's kind of a different name in the different products, but yeah, definitely.
And like that is a big one that I see a lot of people really starting to play around with. I think that over the next 5 to 10 years, you're going to see that really start to take hold in some key niches and maybe some industries. I think we have a long ways to go before we supplant traditional design methodologies with that, though, because it's just such a new frontier. I think there's a lot of people that kind of want to sit back and let some other people take the arrows going up the hill with it before they start going, okay, let's bring this into our workflow or our products or services. So that's a big one. Inside of SolidWorks, we talked about it. That texturing tool, I really, really think that texturing tool is huge. I think that you can bring a lot of really cool design aesthetics to a part that you're designing in SolidWorks using that. And I really haven't seen anything that really works as slick as that does and has the ease of use that tool has inside of SolidWorks for a novice, a non-industrial designer to be able to bring those type of features into a part. I think inside of SolidWorks, those would be the two that really jump out at me as tools that are specifically, you would never use that texture feature for any machined part or casting. Like, I can't think of any other process you would use that for other than a 3D printed part. And same with generative. Maybe casting you can do some generative stuff with, but still, even then, you got to print the patterns because you can't you got to print the cores and because you can't manufacture them any other way.
I think, one of the biggest things that jumps out at me, we talked about this during the live episode, was you can just unlock the way you think about traditional design. I remember seeing specifically NASA designing parts that weren't manufacturable using traditional machining technology. I think they were for fuel delivery or something like that. Yeah. And they were 3D printing out of titanium or something crazy. It was like unreal. Like they were able to really change the way they thought about the design process.
Yeah, it's really a complete mind shift that you got to kind of go through to really take additive and really take it to its full potential as a designer. It's just a completely different way of thinking.
Paul, the next question we kind of briefly touched on before. The question is, how has modern 3D printing adapted to newer technologies like generative design? Tried printing a model created through the same using STA/UV resin, but it didn't turn out quite as expected.
So generative is always going to be challenging when you're using like FDM or SLA. And the reason for that is you have to have supports. And generative makes these crazy kind of almost organic structures. I like to say a lot of times it looks like roots in a tree, right? They just kind of go wherever the simulation tells them to go to get the amount of support that they need. And printing those on FDM or SLA can really get challenging. I would say if you're really going to go hard in that direction, you probably need to be looking more at like the powder bed systems like MJF or SLS, or a polyjet, which again has a very different way of doing supports, but it can deal with those types of structures. Also, like metal printing is not something we've talked about a lot, but generative is very, very much on the come up in the metal printing world for lightweighting, like aerospace and high performance automotive and things like that. We don't do metal printing here, so I'm not going to expound on that too much, but I've seen some very, very cool stuff that some of those metal printing guys are doing where they're using generative design, but they're training they're setting parameters around the generative design so that when it does its generation, it does respect some rules to say that, everything must be above 45 degrees. And if it's going to be come across, it's going to be an arch, so that they can have a lot less support when they go to print them by trying to, stick to those rules.
Paul, during the live presentation, when we were talking about SLA, you shared some unique geometry creation capabilities. You were talking about 45 degrees and kind of the Roman arch. The question that is asked is, how do you calculate the 45-degree angle when the top of the arch goes outside of 45 degrees? And I think we're talking about kind of there are two different specific cases here, right? One being the arch and one being the angled surface.
So I actually got a fair amount of this question after we talked about the arch. And in my experience, if you're going with heavier layers, so in the case of that SLA machine, we can print in 4 thou layers, or we can print in 6 thou layers. And that 2,000ths doesn't sound like a lot of difference, but it actually is. And we found that the software will tell you that you need support in the middle of that arch. But if you're running heavier layers, and this could also go for an FDM machine as well, if you're running those 10 thou or 13 thou layers on an FDM machine, like much heavier layers, it tends to bridge that gap. And sometimes you will have a little bit of failure at the top of that arch. But generally it's just a little bit of a dip. So in this case, it was a pressurized air chamber. So if the top had a little bit of failure, that wasn't going to be a big deal for us. But especially if it's an arch that is, outside, not enclosed, where you could get to the bottom side of it, you could clean that up with a little bit of post-processing work afterwards. But we've successfully run a lot of arches without any support. And, you get down into those finer resolutions, and sometimes they don't turn out. Sometimes those finer resolutions just can't seem to bridge that gap, and you do see failures. But for the most part, it turns out. I'm not going to sit here and tell you it's like perfect every time, but it's perfect most of the time, and it works pretty well for what we do here.
And a lot of these were, you're looking at just specifically in general geometry scenarios that might help you avoid putting support structures on the internals of.
In a case like that blowback block, I will take a little bit of failure if it means I don't have trap support, because my use of it can deal with a little bit of internal failure, but it cannot deal with support inside of there.
All right, Paul. So we have a question here. They ask, does SLA use a mesh of triangular patterns?
Does SLA use a mesh of triangular patterns? I think what they're asking is maybe like the file type. So when you have a part in SolidWorks, it's clean surfaces, nothing crazy going on. As soon as you save it to an STL, it meshes the part. So essentially it goes through and breaks the entire part down into triangles. And sometimes if it's a flat surface, those triangles are huge. And if it's a very complex, organic surface, those triangles are super, super tiny. But when you save a part out as an STL, it does mesh the part. And yes, we would always use an STL file to set up and run builds on machines. No matter what machine, we would be using either an STL, an AMF, or a 3MF file.
Paul, now we have a technical question. When working with STL files inside of SolidWorks, this user asks, How do I convert in assembly in STL? As I'm converting, it just converts the STL into individual parts of that assembly.
Yep. So we run into this all the time. If you go with your assembly, so you have your assembly on screen, you go File, Save As, and then you pick the drop-down file extension for STL. When you do that, there is going to be a button in the lower left-hand side of that pop-up save window called Options. And if you click on Options, it opens the Options menu for STL, 3MF, and AMF files. And all the way down, second from the bottom, there's a checkbox that says Save all components of an assembly in a single file. All you got to do is check that and then hit OK and hit Save, and it will spit everything out as a multi-body STL instead of assembly files or individual files of the assembly.
So there you go. Important tip. Anybody using SolidWorks, if you save any kind of file that is not outside of SolidWorks, if you're exporting a file, basically, you'll want to make sure there's options for every type of file that you can save out of there. And every one of them has their own settings in there. So definitely a good place to look, Paul. Thanks for that tip. So, Paul, during the live stream, we talked about some of the SolidWorks specific features that you use when designing for additive manufacturing. One of the questions is, do you recommend to only make the hole feature and then after the part is done, putting the taps on the holes? Why was that? And there was a very specific reason you talked about this. And let's elaborate on that a little bit.
Yeah. So a helical feature like a thread is an incredibly heavyweight feature for SolidWorks to have to calculate. So, you're going along and you're doing some work and you hit, Control Q to rebuild, or you hit the little stoplight to do a rebuild. Well, now SolidWorks has to go through, and if you've scattered those features throughout your tree, it's got to go through and rebuild every single one of those. And if you have one or two, that's probably not a big deal. But if you have a design that's got 30 or 40 of those, you will see a big performance hit. And it's not necessarily like, oh, your computer's a piece of crap, or, oh, SolidWorks is being slow. Like, no, you just have a really heavy feature in your tree. So what you want to do is you want to put all those at the bottom. You want those and texture to be the last things that you apply to your model. Because then, okay, I'm all the way done. I do a rebuild. Oh, well, my rebuild might have taken a couple of minutes. No big deal. I'm going to do it one or two more times, and I'm saving this out as an STL and sending it to the printer. Versus, if we were to go and, oh, sorry, something popped up on my screen here. Versus if we were to take and put that throughout the tree, you just got all that rebuild time. So save all your rebuild time for the end. Don't put it throughout. But you use the hole wizard so you know exactly, oh, it's going to be this diameter. It's going to be right here. So it's there. You just don't put the thread feature in until the very end of your design process.
Yeah, I mean, this is a very specific reason why SolidWorks in the hole wizard uses a cosmetic thread or a graphic representation for a thread. Is specifically because of the fact that helical features consume a lot of rebuild time and they're graphically intensive to do this. To Paul's point, when you use the hole wizard feature, one of the key things that it does is it allows you to use the drill diameter for that specific size hole as well. So this is a very good representation of that tapped hole, which makes it much easier to put those physical helical threads on it later on. So again, I always recommend this to people using SolidWorks. If you're not using it for 3D printing, use the hole wizard, use the cosmetic threads.
Yes.
But the thread feature, yes. I always recommend saving these super heavy things for the end. I even sometimes, if a fillet doesn't need to be added until the end of a design, don't put the fillets on until the end of the design.
I couldn't agree more.
Paul, we have a question about going back to the thread feature. Is there an easy way to adjust which orientation the thread starts on? I guess I can't think of a scenario where that's important, but you have a lot of experience with the thread feature itself.
So let's say you're doing and this would probably be more for like not like a thread for a fastener, but maybe you're doing like a crazy custom thread for like a screw-on cap for like a big plastic bottle, like a wide mouth bottle. And maybe you have like a spout coming off of that. So you want that spout to start and stop at a certain position on your bottle. I don't know this to be 100% true, but I'm almost positive I've seen the ability to set the position of those threads based off of a 360-degree field. So which degree would you like to use for the orientation of your threads? I'm almost positive that is built in there and that I've used that in the past. But I wouldn't mess around with that for like fasteners. That's more for like plastic joining type applications in my mind.
Paul, during the live stream, this question came up, and I'd like to include it here as well. And the question is can you scale within the thread tool to account for shrinkage? I always have to chase my threads. And there was some conversation during the live stream about, well, this could depend on the technology you're using to print it. And that may ultimately just be something you have to do is chase a thread.
Yeah. So if you're doing desktop printing with like an FDM machine, I think you're always pretty much going to have to chase the threads. Kind of hearkening back to another question that was asked about, the accuracy of machines, right? And every machine runs a little bit different. Every environment's a little bit different. When you get up into more of the industrial scale machines like we have, I mean, we print threads all the time with MJF. And rarely do we have to chase them in order to get them to come out. They almost always come out perfect right off the machine. So yeah, I think that, it also depends on how big of thread you're doing. Like typically on FDM, we don't like to go below like a 1/2-inch thread. We find that it just doesn't really have the resolution to print that fine of thread. Whereas on MJF, we'll go all the way down to 1024 thread sizes, and we have great success. So I think it's sometimes just the machine you use, you're just going to have to do it, but that's okay. It is what it is, and like I said, we chase threads here sometimes too. But yeah, that would probably be the best answer I could give.
So Paul, next we have a couple questions for people who are new to 3D printing, interested in getting involved in them. The first one is if you're new to 3D printing, what are some good resources to help you start learning how to 3D print?
Honestly, the absolute best thing you can do is if you can go get yourself a small printer off of Amazon or something like that, and you can sit at home and just try everything you ever want to try and fail and succeed and win and lose. Honestly, that's how I did it. But let's say that's not an option for you. A lot of public libraries now have like MakerBots or like FDM type machines available for, I don't know, like the one in town here. All you have to do is pay for material, and they get it off Amazon. It's dirt cheap, so you can print to your heart's content for not a lot of money and not have that capital outlay of the machine. A lot of schools, I mean, I know tons and tons and tons of high schools and even some middle schools now where they have 3D printers in like their CAD labs and things like that, or their shop classes. So, if you're a kid, if you're younger, you could probably find something like that at your school. If you're in college, I could almost guarantee pretty much every college that has an engineering department has to have a 3D printer laying around somewhere. It's it's almost required at this point. And so, yeah, so, whether you're, going to the public library or you can find access through your school or education system, I think hands-on is the best way. Now, I can't I've seen some books out there that are like 3D printing for dummies and things like that. Any knowledge is good knowledge, but I would always argue I'm a big hands-on learner. I think additive is the ultimate hands-on thing. Like I actually, after our last conversation, I had a couple young people reach out to me and say hey, I'm getting ready to go to college. I want a career in additive. Where do I go to school for additive manufacturing? And I was like, I don't know. I don't know of a college that has a specific additive manufacturing track that I could point you to. I know there's certificates and stuff like that for an online course, but I really think additive is one of those things, if you really want to learn about this and you want to get into this industry, especially if you're a young person, find some place, go to your local additive manufacturing company and just be bold and go in and say, look, I want to work in this industry. I will push a broom. I will scrub parts. I will do whatever it takes to be involved and work here. And if you walk in and you show that level of interest and that, amount of, go get it attitude, I would be shocked if they couldn't find something for you to do. You probably won't make a lot of money, but I can promise you'll probably learn a ton. And it's that toe through the door, the crack in the door that you need to get into this industry.
Yeah, great information there. I think you know, when it comes to the universities around here, I know there are manufacturing technology courses
Yep.
you can get into where they're going to cover this type of thing as well. I
Yep.
know at the vocational level, you can you know, through your school, go get involved there also. So,
Yep.
what are your recommendations for people who want to get into the 3D printing industry?
Yeah, like I said, you know, there's not a ton of shops out there, relatively speaking. I mean, if compared to like, you know, machine shops or sheet metal fabrication shops or tool and die shops, you know, we have a saying here in Michigan: you're not a real town unless you have a church, a bar, and a tool and die shop. So you know, geography plays a lot into this, right? But you know, additive is on the rise. Additive is becoming more and more of a force to be reckoned with. There's more and more people getting into it. So, like I said, you know, I can only give you my advice, and I've always been the type of guy who, you know, if I wanted to do work in an industry or if I wanted to be involved with something, you know, I would just show up at the place and politely, but still walk in and say, "Hi, my name's Paul DeWys. I'm really, really interested in working in the additive industry. I don't know if you're hiring, but I'll push a broom. I'll wipe down parts. I'll do whatever it takes." And that's how I did it. It worked out pretty well for me. You know, but also, you know, you've got big organizations, big companies, you know, Ford, you know, GM has a new additive center of excellence that they just opened in Warren. You know, Lockheed or Northrop Grumman, they all have these huge additive businesses or you know, business units inside of them, just serving their own engineers' needs. You know, and I mean, if you get on LinkedIn and you start putting in some keywords and kind of connecting some dots, you can find people in these bigger organizations. So maybe you are a kid who's about to graduate with a bachelor's in mechanical engineering or a master's in mechanical engineering, and you want to go and work in one of these Fortune 250 companies that have additive in their businesses. You know, the internet is a powerful thing. It's incredible the people that you can track down and connect with. I would say it's all about just putting in the time and being willing to, you know, hey, you know, you can sit here on a Saturday and you can go play softball, or you can go, you know, walk in the park, and those are great things. But you could also spend a couple hours on LinkedIn and find the head of additive for Ford, and then pester him relentlessly until he either blocks you or gives you an opportunity. So, you know, that would be my advice. Like, be tenacious. If you want something, find a way to kick down the door, even if they won't open it for you. Don't
Very
actually
good.
kick down anyone's door. That was a metaphor.
So the next question goes right along with this, and you just mentioned it. What's a good starter 3D printer? You mentioned the Mark Forge as that. So, but maybe I don't work for a company. Maybe I'm like on my own. Anything else? Like, so you're kind of in that mid-tier price range. What about like the really low-tier price range? We did talk about this on live a little bit, just kind of Amazon searching for these things.
So I'll be honest. My knowledge base doesn't really go much below a Markforged or a Formlabs. Formlabs would be the other one, and I really should have shouted them out in the last question too. If you're doing more product development or medical device or things like that, Formlabs would probably be maybe something you should look more at than maybe a Markforged would be. But really, unfortunately, I can't really speak to anything kind of further down the kind of consumer friendly technology stack than that. You know, but I tell you this. There's a bunch of guys on YouTube reviewing every single machine that comes out and being brutally honest about it. So if you find a $300 FDM machine or a $200 SLA machine on Amazon, you're like, man, I don't know, are all these Amazon reviews fake? Is this thing legit? Take that name, punch that into YouTube, and put review behind it, and I bet you find 3-4 pages of people saying everything they love and everything they hate about that machine. Watch 3 or 4 reviews, kind of average them together, and that should tell you what you need to know about the machine you're looking at.
Yeah, I know. I have 2 personal friends. They I have nothing to do with engineering whatsoever. One works at a restaurant and one is an IT specialist. They both bought Enders and they love them. They think they're like the greatest thing in the world.
Enders are a sweet machine. We're working on an Ender for a customer out here, doing a really cool dispense head for it. They're great machines, and for what you pay for them, it's like, I can't believe you can get a machine this cheap that does this good of work.
So we're going to dive a little bit into the secret sauce about what makes Forerunner 3D printing here. It says, how do you start a business in 3D printing, or how can we start our own? What are some of the basic requirements to start a 3D printing business? And, you know, I think in my mind, one of the first thing, you know, when I've visited your facility was a massive investment in capital equipment.
Yep. Take $1 million, get it in cash, put it in the middle of your parking lot, light it on fire, watch it burn, and then go try and form your business. No. Yeah. Okay. So I've actually gotten this question from a couple of people after we talked, and I've been kind of dwelling on it a little bit. So our journey into additive was so odd, I guess. You know, we started as an engineering company, and you know, we did that for 5 years, and you know, I had a MakerBot, and I was trying to use that MakerBot anywhere I could, honestly, just because I thought it was so cool, and I thought there was potential there, but I didn't really fully grasp the complete potential. And then I had that opportunity to acquire one of our vendors, and that was just kind of a happy accident. I was there, right time, right place, and you know, had the guts to say, yeah, let's do it. I'm going to buy this company from you. And I mean, I will not lie. I mean, our 3D printing business unit, Forerunner, I mean, we were unprofitable for the first 3 years. Our engineering business kept our 3D printing business alive because literally I didn't know. I literally was making it up as I was going. I bought this company. I didn't really know anything about it. And it was just every day I was just learning and learning and learning. And it took years to get to the point where all of a sudden, okay, I've made pretty much all the mistakes. So now I'm done making mistakes. We can start, you know, really starting to crank things up, and then, you know, buying more equipment, buying bigger equipment. You know, and so I really think, and I know of a couple other people that literally started with a MakerBot in their spare bedroom at home and built additive manufacturing companies from the ground up. But you know, it's going to take a lot of work. It's going to cost you a lot of sleepless nights. You got to put a lot into it, both, you know, personally and financially. So to build an additive business from the ground up is totally doable. But it's a long, hard trail to get there. But the great thing about it is this industry is, you know, it started in the late 1980s, early 1990s. When I was casting around in the you know 2014-15 area, wanting to expand beyond engineering, I was like, maybe I start a machine shop, maybe I get into foundry, maybe I buy an injection mold press, you know, maybe I do cast urethane. And every time I got into one of those industries and started looking at it, I mean, foundry industries, I mean, there's like 4th and 5th generation family businesses from like the 1870s that are in the foundry industry. You know, machine shops, CNC machine shops, there's guys that were, you know, at the very cutting edge in the 1970s, early 1970s with the old, you know, tape-based machines and stuff. And I looked and I'm like, how am I ever going to break into one of these industries? You know, and then I saw additive and it was like, oh, this is like still sort of new. Like there's big players, don't get me wrong, but there's not as many big incumbents and there's not as many long multi-decade relationships as there are in other manufacturing areas. So I kind of looked at that as like, you know what? I think this is a great tie-up with my engineering business, and I think that there's a real opportunity here because there's still plenty of green grass and blue sky for me to go out and try and grab my piece of. And I mean, I know plenty of guys that are starting CNC shops very successfully nowadays, but for me, I just saw additive as like an open space that I could go in that really tied up nicely with my existing company.
I love this question. This is one of our favorite questions we get on SolidWorks Live and SolidWorks Live Design. Describe the most interesting fixture you've made and what made it great.
Ooh, that is a good question. I think I have some recency bias on this because we're actually designing this machine right now. But let's just say there is a very large automotive OEM who has a very popular pickup truck. And let's just say hypothetically, maybe that pickup truck has an electric version of it coming out. And if it's an electric version, you probably need a place to plug that thing in. And that would mean that you have a door and you have to open that door to get to the plug, hypothetically speaking. And we had the opportunity to design the machine that actually puts this hypothetical product together. And so it was really, really cool to see, like, you know what, like every time you walk by one of these trucks, you're going to see this right on the side of it, and you're going to know that that came off of not only a piece of equipment we designed, but all the fixturing was TPU rubber printed because it's all chrome. So, so yeah, that's one we're working on right now. That was really cool. You know, we do a lot of, we're in Western Michigan, so automotive is big here. You know, we've worked on stuff for pretty much, you know, all the major automotive companies and platforms. It's always cool to do stuff for like Cadillac or Corvette or things like that, you know, especially when it's like a Class A part where you know it's going to be on the exterior of the car, and you know you're walking through the parking lot, you know, the grocery store or whatever, and you walk by a vehicle and you go like, I guarantee you that came off of a piece of equipment I had a hand in. So yeah, I would say that hypothetical electric pickup truck is probably the coolest thing we've worked on.
Very cool. Always one of our favorite questions we get. You know, people probe you like, what do you really like? Because we all do really cool things here.
Yes, absolutely.
Very similar question. Maybe you can just say ditto on this one. What is the coolest or most involved 3D design you've created?
So this is outside of our additive business. Has nothing to do with our additive business actually, but has everything to do with Solidworks because the whole thing was done in Solidworks. One of our customers is a very large aerospace foundry, and next time you watch SpaceX land one of their rockets out on the drone ship, you'll notice that they have some giant grid fins that pop out at the top that they use to steer. Our customer cast those for SpaceX. And it was one of those projects where everyone was way behind, and the customer is very, very demanding. And so we had to add casting stock. So when you cast something, it shrinks. So you have to go through and add stock so that when it shrinks, and then also there was some very, very advanced post-processing, we'll say, that you also had to account for with that shrink. So essentially you take the model that was provided by the customer, which in this case would have been SpaceX, and then you have to add stock in very specific amounts and very specific directions. And we had about 24 hours to do it. So my engineering manager took the first shift, and he worked from 6 a.m. in the morning until about 6 p.m. at night. And then I tapped in and worked from 6 p.m. at night until 6 a.m. the next morning. And in 24 hours, we were able to get this entire thing stocked out. And it was all surfacing in SolidWorks. I mean, I've never used the surface offset command so many times in my life. And I mean, in that night, like, you go through like the complete life cycle of just like, things are going great. This is really easy. And then you like paint yourself into a corner and you can't get something to knit. And you're just like, oh my God, I'm going to have to start completely over. And then it's like, oh, I got it figured out and things are looking good. So you go through that cycle like 4 times in one night, and you're just like wrecked on like Red Bull and just like, eating chips and trying not to fall asleep at your desk. But like, that was one of the coolest things ever, because it was like the most advanced surfacing project I've ever done in SolidWorks, full stop. But also, to be able to say we got it done on time for the customer, and and now every time one of those things is landing, I get to look at it and go, I had a small little micro tiny piece of that grid fin right there. So that would be probably the coolest thing I've done in SolidWorks, not necessarily involving additive.
Well, Paul, this was a really fun session, kind of answering all of our audience's question from last week's SolidWorks Live. I want to thank you for joining on this special Q&A session where we got to talk more about additive manufacturing. If people want to learn more, reach out to you, where can they go?
So you can always go and check out our website, forerunner3d.com. So that's FORERUNNER, the number 3 and the letter D.com. A lot of cool R&D videos on there. If you want to reach out to me directly, it's paul@forerunner3d.com. And I'm super active on LinkedIn. Love getting connected with people on LinkedIn. Even if we've never met in person or talked, feel free to shoot me a connection request. All you got to do is just look up Paul DeWys on LinkedIn. So that's PAULDEWYS on LinkedIn, and shoot me a connection request, and feel free to send me questions. But Jeremy, thank you to you and the entire SolidWorks team over there for giving me another opportunity to come back and talk with everyone about 3D printing. I love doing this stuff. So thank you so much for the opportunity.
All right, thanks, and stay tuned. If you want to see more great content like this, make sure you subscribe to our YouTube channel. And if you hit that bell notification icon, you won't miss any of our episodes that are live every Thursday at 11 a.m. Eastern Time.